Imagine this. You're holding a warm teacup. Sunlight glints off its porcelain curve. You lift it to your lips and your hand slips. It falls. For a heartbeat, it hangs in the air, suspended, fragile, perfect. Then it hits the floor. Crash, shards scatter. Tea splashes across the tiles. Steam curls upward, vanishing into the air. Now, try to unbreak it. Not with glue, not with magic, but with the raw laws of physics alone. Imagine every molecule of porcelain reversing its path, flying back together. Every droplet of tea leaping from the floor, reassembling into a swirling liquid column, rising into the cup. The steam condensing, rushing back into the vessel. The cup lifting itself into your hand, whole again. It feels impossible, not just difficult, wrong. As if the universe itself would recoil at the sight. And yet, here's the mystery. If you filmed that broken cup and played it backward, every single motion you'd see, the shards leaping, the liquid rising, would obey the exact same laws of physics that govern the forward version. Newton's equations don't care. Electromagnetism doesn't flinch. Even quantum mechanics, at its core, treats past and future with eerie symmetry. So why can't it happen? Why does time feel like a river that only flows one way, carrying us from birth toward decay, from order toward mess, from memory toward forgetting? We've all felt it. The ache of a moment lost. The frustration that yesterday can't be rewritten. The quiet dread that tomorrow is unwritten, but yesterday is sealed in stone. Time doesn't just pass. It points. It has a direction. An arrow. But arrows need a bow. A reason to fly forward and not back. And for centuries, scientists searched in vain for that bow in the wrong places, in the ticking of clocks, in the spin of planets, in the fall of apples. They found perfect symmetry, perfect reversibility. A universe that, on paper, should run just as happily in reverse. Then, in the smog-choked factories of the 1800s, a quiet revolution began, not in telescopes or particle colliders, but in steam engines. Men like Rudolf Clausius and Ludwig Boltzmann weren't studying stars. They were studying heat, efficiency, waste. And in the hiss of escaping steam, they stumbled upon something far deeper than engineering. A hidden law woven into the fabric of reality itself. A law that doesn't care about position or velocity, but about possibility, about how many ways things can be arranged, about disorder. That teacup didn't break because gravity demanded it. It broke because there are countless ways for porcelain to lie in shards, and only one way for it to sit whole in your hand. The universe doesn't forbid the cup from reassembling. It's just astronomically unlikely. So unlikely that if you watched every teacup in every galaxy for longer than the current age of the cosmos, you'd never see it happen once. And that is where time's arrow is born. Not in force, not in motion, but in chance. In the silent, statistical pull toward chaos. This is the heart of our story. A law that says going back is so improbable, it might as well be forbidden. And yet, this raises a deeper question. If the arrow of time comes from disorder increasing, then why was the universe ever ordered to begin with? Why did it start in such a pristine, unlikely state, like a teacup held perfectly still in empty space, just waiting to fall? To answer that, we must leave the kitchen, leave Earth, leave even our galaxy. We must travel back to the very first flicker of existence. Because the reason time cannot go back is written in the first breath of the cosmos itself. But before we go there, we must first understand why the laws of physics, so elegant, so symmetric, seem to hide this arrow entirely. why, in their purest form, they are blind to past and future, and how one quiet equation betrayed them all. Close your eyes. Imagine the universe as a vast, silent clockwork, gears of gravity turning, springs of electromagnetism coiling and uncoiling. Every planet, every atom, every photon moving according to rules so precise, so elegant, that if you knew the position and speed of everything right now, you could, in theory, calculate every moment that ever was and every moment that ever will be. This was the dream of Isaac Newton, a cosmos of perfect predictability, a universe without memory, without preference, without direction, and for over 2 centuries it held. Drop a ball, it falls. Film it. Play it backward. The ball rises, slowing as it climbs, exactly as Newton's laws allow. No violation, no alarm bells. The math works both ways. Now imagine 2 billiard balls colliding. In forward motion, they strike, ricochet, spin away. In reverse, they come from opposite corners, meet at a point, and fly back along their original paths. Again, perfectly valid. The equations don't flinch. Even when James Clerk Maxwell unified electricity and magnetism into a single, shimmering theory of light, the symmetry held. His equations describe waves rippling outward from a source, like ripples from a pebble dropped in a pond. But mathematically, they also permit waves, converging inward, ripples rushing toward a point, gathering energy and vanishing into nothing. We never see that, but the math allows it. Then came Einstein. With his theory of relativity, he wove space and time into a single fabric, space-time. And still the equations remained time-symmetric. Flip the sign on time, and the cosmos hums along just the same. Black holes form. In reverse, white holes erupt, exotic. Yes, forbidden, not by the math. So where is the arrow? If every fundamental law from gravity to quantum fields treats past and future as equals, why does our lived reality scream otherwise? Why do we age but never grow younger? Why do stars burn out but never spontaneously ignite from cold ash? Why do we remember yesterday but not tomorrow? The answer isn't in the laws themselves, it's in what the laws leave out. Think of a law like a recipe. Newton's laws tell you how ingredients move once mixed, but they don't tell you how the ingredients were arranged before you started cooking. The laws are the rules of the game, but the initial conditions, the starting position, are the real storyteller. And in the case of our universe, the starting position was astonishingly special. For a long time, physicists assumed this was just a coincidence. Maybe the universe began in chaos and we're just in a lucky pocket of order. But that doesn't hold up. Because if the universe had started in maximum disorder, what physicists call thermal equilibrium, then nothing would ever happen. No stars, no life, no broken teacups. Just a lukewarm soup of particles, evenly spread, with no gradients, no differences, no change. Time would exist, but it would be meaningless. Like a clock with no hands. Hot stars against cold void. Dense galaxies in empty space. Ordered DNA in chaotic oceans. These differences are the engines of change. They drive everything from photosynthesis to supernovae. And all of them trace back to one thing, a state of extremely low entropy at the beginning. Entropy. That's the ghost in the equations. Not a force, not a particle, but a measure of how many microscopic arrangements correspond to the same macroscopic state. A shuffled deck has high entropy, many ways to be mixed. A new deck, ordered by suit and rank, has low entropy, only one way to be perfect. The second law of thermodynamics says, in a closed system, entropy tends to increase or stay the same. It doesn't say it must. It says it's overwhelmingly likely, and that likelihood, born from statistics, not force, is what gives time its direction. But here's the twist. The second law isn't a fundamental law like gravity, it's emergent. It arises from the behavior of countless particles obeying time-symmetric rules. So the arrow of time isn't written in the bedrock of physics. It's written in the initial condition of the universe, and that condition, low entropy at the Big Bang, is the true origin of why we can't unbreak the teacup. Yet this raises a deeper puzzle. Why was the early universe in such a low entropy state? Of all the possible ways the cosmos could have begun, chaotic, uniform, high entropy, why did it choose the one so improbably ordered? It's like finding a pristine sandcastle on a beach after a hurricane. The laws of physics explain how waves erode castles, but they don't explain why the castle was there in the first place. Some have called this the past hypothesis, the idea that the universe began in a state of very low entropy and that this boundary condition is what breaks the symmetry of time. Without it, the second law wouldn't point anywhere. With it, time acquires a spine, a direction, a story. But is the past hypothesis just a convenient assumption, or is there a deeper reason? A cosmic mechanism that set the stage for time's arrow. To find out, we must journey into the realm of chaos. Not the chaos of noise or destruction, but the chaos of sensitivity, where the tiniest whisper can become a hurricane, where the future explodes with possibilities, but the past collapses into a single thread. Because even if the laws are symmetric, the behavior of complex systems is not. And in that asymmetry, time finds another voice. Picture a single drop of ink falling into a glass of still water. At first, it holds its shape, a dark pearl suspended in clarity. Then slowly, tendrils reach outward. Swirls form. The ink spreads, diffusing, blending, until the water is uniformly gray. Now imagine reversing that. The gray water suddenly stirs. Ink gathers from every corner, spiraling inward, collapsing back into a perfect droplet that leaps out of the glass and returns to the bottle. Absurd, right? Yet every molecule in that water obeys Newton's laws, laws that don't care about direction. So why does the forward process feel inevitable and the reverse feel like sorcery? The answer lies not in the laws, but in sensitivity, in the way complex systems amplify the tiniest differences into vast consequences. This is chaos, not as in disorder, but as in deterministic unpredictability. In the 1960s, meteorologist Edward Lorenz was running weather simulations on an early computer. He typed in a number, 0.506. The model churned out a forecast. Later, he reran the same simulation, but this time he entered 0.506127, thinking the extra digits wouldn't matter. They did. The new forecast diverged wildly from the first. A butterfly flapping its wings in Brazil, he realized, could set off a tornado in Texas, not because of magic, but because the atmosphere is exquisitely sensitive to initial conditions. This became known as the butterfly effect. But here's what's rarely said. The butterfly effect only works forward in time. Run a chaotic system backward, and something strange happens. Instead of amplifying differences, it erases them. Imagine tracing the path of smoke rising from a candle. Forward, it twists, forks, dances, infinitely complex. Backward, all those chaotic tendrils must converge perfectly into a single, smooth column returning to the wick. For that to happen, every air molecule would need to reverse its motion with impossible precision. The slightest error smaller than the width of an atom, and the smoke would fail to reassemble. In forward time, chaos creates information branching possibilities, new structures, irreversible patterns. In reverse time, chaos destroys the possibility of reconstruction. This is why spilled milk doesn't jump back into the glass. It's not just that there are more disordered states, it's that the path from order to disorder is robust. Many starting points lead to the same messy end, but the reverse path is fragile. Only one exact configuration of trillions of molecules could make the milk leap back, and the universe doesn't keep that blueprint. Once the information is scrambled, once the ink diffuses, once the teacup shatters, it's not gone, technically, but it's hidden in correlations so fine, so entangled, that no practical observer could ever recover it. This is the link between chaos and entropy. Entropy increases not because particles want to spread out, but because spreading out is the only outcome that doesn't require impossible coordination. Chaos ensures that once a system explores its possibilities, it almost never returns to where it began. And that's why time has a memory of the past, but not of the future. But here's a haunting thought. If you could reverse the velocity of every single particle in the universe, flip their directions like rewinding a film, would time actually run backward? In theory, yes, the equations allow it. In practice, no, because to do that, you'd need to control every particle with infinite precision, and the moment you missed even one by less than a trillionth of a degree, the chaos would take over, and the system would veer off into a new future, not the old past. The arrow isn't in the particles, it's in the impossibility of perfect reversal. This fragility is why we can trust records, why fossils, tree rings, ice cores, and light from distant stars all point in the same temporal direction. They are all products of irreversible processes that leave traces only when entropy increases. A footprint in sand doesn't form when wind blows away from a shoe. It forms when the shoe presses into the sand, increasing disorder at the microscopic level, even as it creates macroscopic order. Time's arrow isn't just about messiness. It's about causality, about cause always preceding effect. And chaos ensures that causes leave ripples that cannot be perfectly gathered back. Yet even chaos and entropy together don't fully explain why the universe started in such a special state. Because if the laws are symmetric and chaos only amplifies forward, then the ultimate source of time's direction must lie before chaos began. At the very beginning. In the first fraction of a second after the Big Bang, when the entire cosmos was smaller than a grain of sand, hotter than the core of any star, and smoother than any surface we can imagine. That smoothness, that near-perfect uniformity, was the ultimate low-entropy state. But why? Why didn't the universe begin lumpy, chaotic, high entropy, as random chance would suggest? To answer that, we must confront the most mysterious moment in cosmic history, the moment when time itself took its first breath, and in that breath, set the arrow flying forever forward. Before there were stars, before atoms, before light could travel freely, there was only heat, an ocean of energy, seething, dense, unimaginably hot. The entire observable universe compressed into a volume smaller than a marble. No edges, no outside, just pure radiant potential. And yet, in that inferno, something astonishing was true. It was smooth, not perfectly smooth. Tiny ripples existed, quantum whispers imprinted in the fabric of space-time. But compared to what it could have been, compared to the violent, lumpy chaos that randomness would predict, this early universe was eerily calm, like a still pond at dawn, and that stillness was the seed of time's arrow. Entropy isn't just about mess. It's about how many ways you can arrange the pieces without changing the big picture. A room full of gas molecules has high entropy if the gas is spread evenly, because there are countless microscopic arrangements that all look like uniform gas. But if all the gas is squeezed into one corner, that's low entropy. Only a few arrangements look like that. Now apply this to gravity, the force that dominates the cosmos. Here's the twist: for gravitating systems, smoothness is low entropy, clumpiness is high entropy. A uniform cloud of gas has lower gravitational entropy than a universe full of black holes, because black holes represent the ultimate gravitational disorder, regions where matter has collapsed into the densest possible configurations, maximizing the number of hidden microstates. So when the early universe was smooth, hot, and nearly uniform, it was in an extremely low entropy state. Not because it was tidy, but because gravity hadn't yet had the chance to clump matter into stars, galaxies, and black holes. This is the key most people miss. If gravity didn't exist, a uniform gas would be maximum entropy equilibrium. But gravity changes everything. It's an attractive force that amplifies differences. A slightly denser region pulls in more matter, becoming even denser. A void becomes emptier. So the true high entropy end state of our universe isn't a lukewarm soup. It's a sky full of black holes slowly evaporating into cold, empty space. And we are still on the long, slow journey from smooth beginning to clumpy end. But why did the universe begin so smooth? Why didn't it start as a frothing sea of black holes? Random, chaotic, high entropy. That would have been vastly more probable. Imagine shuffling a deck of cards. The odds of getting them in perfect order are 1 in 8 times 10 to the power of 67. Now imagine the odds of the entire universe beginning in a smooth, low entropy state. They're far, far worse. So why did it happen? In the 1980s, physicist Alan Guth proposed an answer: cosmic inflation. A fraction of a second after the beginning, around 1/trillionth of a trillionth of a trillionth of a second, the universe underwent a phase of exponential expansion. Space itself stretched faster than the speed of light, smoothing out every wrinkle, diluting every irregularity, like blowing up a crumpled balloon until its surface appears flat. Inflation explains why the cosmos looks so uniform on large scales. Why the cosmic microwave background, the afterglow of the Big Bang, has almost the same temperature in every direction, to within 1 part in 100,000. But here's the deeper implication. Inflation didn't just create smoothness. It reset entropy. By stretching space so violently, it wiped the slate nearly clean, leaving behind a universe primed for structure, for stars, for life, and for time's arrow. Yet inflation itself raises a new question: what set it in motion? What determined the initial conditions for inflation to begin? Because if inflation requires its own low entropy starting point, then we've only pushed the mystery back one step. Some physicists, like Roger Penrose, argue that inflation doesn't fully solve the problem, that the smoothness of the early universe remains the deepest clue we have about the origin of time's direction. He calls it the Weyl curvature hypothesis, the idea that at the Big Bang, the gravitational field was constrained to be nearly flat, with zero Weyl curvature, which describes tidal forces and gravitational waves. In other words, No black holes, no ripples, just pure, quiet expansion. And that constraint, whatever its origin, is what made entropy low and time directional. So the arrow of time doesn't come from a law, it comes from a boundary, a one-time condition at the birth of everything. Without that special beginning, there would be no distinction between past and future, no cause and effect, no memory, no story, just eternal, featureless equilibrium. But if the universe began in such an improbable state, does that imply design? Not necessarily. Some theories, like the multiverse, suggest our universe is just one bubble in a vast cosmic foam. Most bubbles are chaotic, high entropy, lifeless. But in a near-infinite ensemble, a few will, by chance, begin smooth. We live in one of those rare bubbles, because only in such a place can observers arise to ask the question. It's not magic, it's selection. Still, the mystery lingers. Why this boundary? Why this arrow? And what happens when the universe finally reaches maximum entropy? When all stars have burned out, all black holes have evaporated, and even protons have decayed into dust. Will time lose its meaning then? Or will it keep flowing into an endless, empty future? To glimpse that fate, we must look into the darkest objects in existence, where gravity wins, where entropy reaches its peak, where time itself seems to stop. Black holes. Imagine falling toward a black hole. Not the Hollywood kind with swirling vortexes and screaming violins, but the real thing, a region of space-time so warped by gravity that nothing, not even light, can escape once it crosses the event horizon. As you approach, time begins to stretch. To an outside observer, you appear to slow down, your image reddening, fading, freezing, just at the edge, never quite crossing. But from your perspective, you fall right through. And in that moment, something profound happens to information, to memory, to time itself. For decades, black holes were thought to be entropy's dead ends. Perfectly smooth, featureless pits that swallowed matter, energy, and all traces of what fell in. Then, in the 1970s, Stephen Hawking made a shocking discovery. Black holes aren't completely black. Due to quantum effects near the event horizon, they emit a faint glow, now called Hawking radiation. And over unimaginable timescales, they slowly evaporate. But this raised a crisis. If a black hole forms from a star, a complex object full of atoms, structure, history, and then evaporates into random, featureless radiation, what happened to all that information? Did it vanish? And if so, does that violate quantum mechanics, which insists that information can never be truly destroyed? This became the black hole information paradox, a clash between gravity and quantum theory that shook physics to its core. The resolution, emerging decades later, came from an unexpected place: entropy. In the 1990s, physicist Jacob Bekenstein proposed, and Hawking later confirmed, that black holes have enormous entropy. Not just a little, not even a lot. A single black hole's entropy can exceed the entropy of all the stars in the observable universe combined. How? Because entropy, in this context, counts the number of microscopic quantum states that correspond to the same macroscopic black hole, same mass, charge, spin, and there are staggeringly many. In fact, the entropy of a black hole is proportional to the area of its event horizon, not its volume. A radical idea that led to the holographic principle, the notion that all the information within a region of space might be encoded on its boundary, like a cosmic hologram. This means black holes aren't entropy destroyers. They're entropy maximizers. They represent the most disordered state gravity can produce. and that makes them the ultimate destination of time's arrow. Think back to the smooth early universe, low gravitational entropy. Over billions of years, gravity pulls matter together. Gas clouds collapse, stars ignite, galaxies form, and eventually, some stars die as black holes. Each step increases gravitational entropy. The universe is still climbing the entropy ladder, and black holes are near the top. But here's the eerie part. Once something crosses the event horizon, it's causally disconnected from our universe. No signal, no light, no influence can reach us from inside. From our perspective, the past of that infalling object is sealed away, frozen at the horizon, encoded in subtle quantum correlations in the Hawking radiation. In a very real sense, the black hole erases the detailed history of what fell in. Not by destroying information, modern physics suggests it's preserved, scrambled beyond recognition, but by making it inaccessible. And that inaccessibility is the essence of the thermodynamic arrow. Time's direction isn't about what can happen, it's about what we can know. We remember the past because it left traces. Photons that reached our eyes, sound waves that vibrated our ears, neural patterns etched in our brains. But the future leaves no traces. Black holes take this to the extreme. They are cosmic vaults where the past is locked away, not lost, but hidden so deeply that reconstructing it would require measuring every particle of Hawking radiation over trillions of years with impossible precision. Practically speaking, it's gone. And that's enough to give time its bite. Even more haunting, if you fell into a black hole, your personal timeline would continue until tidal forces stretched you into spaghetti. But to the rest of the universe, your story ends at the horizon. Your future is cut off. Your past becomes a whisper in the radiation. In this way, black holes don't just bend space-time, they fracture time's continuity across observers. And yet, they also point toward time's ultimate fate. Because in the far, far future, after the last star flickers out, after galaxies have drifted apart beyond visibility, the dominant structures in the cosmos will be black holes. They will slowly evaporate one by one over timescales so vast they defy comprehension, 10 to the power of 100 years. And when the last black hole vanishes in a final puff of radiation, the universe will reach maximum entropy. No gradients, no differences, no free energy. Just a thin, cold sea of photons and particles, evenly distributed forever. In that state called heat death, time will still exist, but it will have no arrow, no cause, no effect, no memory, just an endless, featureless now. But we are not there yet. We live in the golden age of structure, between the smooth beginning and the empty end. An era where entropy is rising, but not yet maxed out, where stars burn, where life thinks, where teacups break and we feel the weight of their loss. And that feeling, that ache of irreversibility, it's not a flaw in the universe, it's a signature of our place in cosmic history. A reminder that we exist in the brief, luminous interval when time still has a story to tell. But what about time itself? Is the flow we feel real? Or is it an illusion created by our brains, stitching together moments in a static block of space-time? To answer that, we must confront Einstein's most unsettling revelation, that now doesn't exist. Not in the way we think it does. You're sitting in a quiet room. Outside, rain falls. A clock ticks. Your breath rises and falls. In this moment, it feels undeniable. Now is real. The past is gone. The future hasn't happened. Only this instant. The present is alive. But what if I told you that now is not a feature of the universe, but a feature of you? In 1905, Albert Einstein published a theory that shattered time as we knew it. Special relativity didn't just change how we measure seconds and hours, it dissolved the idea of a universal present. Here's how. Imagine two lightning bolts striking the front and back of a moving train. To a person standing on the platform, the strikes happen at the same time. But to someone sitting in the middle of the train, the bolt at the front hits first, because they're moving toward its light signal and away from the rear one. Both observers are correct. There is no true simultaneity. No now is absolute. Einstein later wrote to the family of his deceased friend, Michele Besso, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." He wasn't being poetic. He was stating a consequence of his equations. In relativity, space-time is a four-dimensional block, fixed, unchanging. Every event that ever happened or ever will happen already exists in this block, like frames in a film reel. Your birth, the formation of the sun, the last breath of the last human, all are equally real, just located at different coordinates. Time doesn't flow, we just move through it. So where does the feeling of passage come from? If the universe is a frozen landscape of events, why do we experience it as a river? The answer lies not in space-time itself, but in thermodynamics, in entropy. Because while relativity erases a universal now, it does not erase the thermodynamic arrow. Every observer, in every reference frame, still sees entropy increase in what they call the future. Your local experience of time's direction is tied to the increase of disorder in your immediate environment. Your brain processing signals, your heart pumping blood, photons scattering off your skin. Relativity says, there is no cosmic clock. Thermodynamics says, but your clock still ticks forward. Think of space-time as a mountain range. Relativity describes the shape of the peaks and valleys, unchanging, eternal. But you are a hiker, starting at a high, smooth peak, the Big Bang, and walking downhill toward a flat plain, heat death. The landscape doesn't change, but your journey does. And the reason you only walk one way? Because the path behind you is steep and narrow, low entropy. The path ahead is wide, branching, full of possibilities, high entropy. You can't go back, not because the mountain forbids it, but because going back would require retracing every footstep with impossible precision, undoing every stumble, every breath, every thought. Chaos won't allow it. This resolves the tension. Relativity kills the universal present. Thermodynamics gives each observer their own arrow. And consciousness, our sense of now, rides that arrow like a surfer on a wave. The wave isn't moving through water. The water is the wave. Similarly, the flow of time isn't something that happens to the universe. It's something that happens within it, through the irreversible processes that link cause to effect, memory to anticipation. But here's the wonder. Even in a block universe, meaning isn't lost. Because your path through space-time is real, your choices leave ripples in the fabric of cause and effect. The love you give, the ideas you create, the teacup you hold before it falls. These are not illusions. They are patterns in the block. And because entropy increases along your world line, those patterns have direction. They have consequence. So yes, physics says the future is already there, in the same way Paris is already there, even when you're in New York. But you still have to take the journey. And the journey only goes one way, not because the map is drawn, but because the road is made of broken teacups, fading stars, and memories that can't be unmade. Yet some wonder, could quantum mechanics offer a loophole? A way for the future to influence the past? for time's arrow to bend, if not reverse. It's a tantalizing idea, one that has haunted physicists for a century. And in the quantum realm, where particles exist in superpositions and entanglement defies distance, perhaps, just perhaps, time is not as rigid as it seems. Deep in a laboratory, a single photon is fired toward a beam splitter, a half-silvered mirror that sends it down two paths at once. According to quantum mechanics, the photon doesn't choose. It exists in a superposition, both paths simultaneously. Only when it's measured does it decide where it's been. Now imagine this. What if the choice of how to measure it made after? The photon has already passed the splitter, could retroactively determine which path it took. This isn't science fiction. It's the essence of the delayed choice experiment, first proposed by John Wheeler in the 1970s and confirmed in labs decades later. In these experiments, the past of a quantum particle seems to change based on future decisions. It's as if time flows both ways, at the quantum level. This has led some to whisper a radical idea: maybe time's arrow isn't fundamental. Maybe it's just an emergent property of large systems, like temperature or pressure. While at the smallest scales, time is symmetric, fluid, even negotiable. Could the future influence the past? Could time heal itself, rewriting history to preserve consistency? The notion isn't new. In the 1945s, physicist Richard Feynman proposed that antimatter could be viewed as ordinary matter moving backward in time. His diagrams, now foundational to particle physics, treat positrons as electrons traveling into the past. It was a mathematical trick, yes, but a powerful one, and it worked. Then came the transactional interpretation of quantum mechanics, proposed by John Cramer in the 1980s. In this view, every quantum event involves a handshake between waves sent forward and backward in time. The present is shaped by an agreement between past and future. Again, interpretation, not proof, but intriguing. More recently, experiments in quantum retrocausality have tested whether future measurement settings can affect earlier particle states without violating causality. Some results hint at subtle correlations that defy classical explanation, though none allow sending messages to the past or changing recorded history. Crucially, even in these models, macroscopic irreversibility remains intact. You still can't unbreak the teacup. Why? Because quantum weirdness is fragile. It survives only in isolation, shielded from the noisy, entangled world. The moment a quantum system interacts with its environment, it decoheres. Superpositions collapse. Probabilities become facts, and entropy rises. This is the key. Quantum mechanics may be time-symmetric in its equations, but the act of measurement introduces irreversibility. When a photon hits a detector, it triggers a cascade. Electrons move, currents flow, heat dissipates. That chain of events increases entropy. And once entropy increases, the process can't be undone. Not practically, not statistically. So even if the microscopic laws flirt with time symmetry, the macroscopic world remains firmly arrowed. Some have hoped that quantum gravity, the still elusive theory uniting general relativity and quantum mechanics, might reveal a deeper layer where time emerges from something more fundamental. In loop quantum gravity, time may disappear entirely from the basic equations. In string theory, time could be a holographic projection from a timeless boundary. But in every serious proposal, the thermodynamic arrow reappears when the universe becomes large and classical. Because without a low entropy beginning, none of these theories produce a universe like ours. So can time heal? Can the future reach back and mend a broken past? The answer, as best we know, is no, not in any way that matters to us. Quantum mechanics offers strange echoes of backward influence, but they are whispers drowned out by the roar of entropy. They cannot restore a lost loved one. They cannot undo a war. They cannot reassemble a shattered moment. And perhaps that's not a flaw, but a necessity. Because if the past were mutable, cause and effect would dissolve, trust would vanish. Responsibility would mean nothing. The very structure of meaning depends on time's irreversibility. Yet the human heart keeps asking, what if? What if we could go back? What if we could fix it? That longing is part of what makes us human. But physics suggests the universe answers with quiet firmness. You can't go back. But you can move forward differently. And in that forward motion, in the irreversible act of choosing again, lies our only real power, which brings us to the most intimate arrow of all, not the one in stars or equations, but the one in our minds, the arrow that lets us remember yesterday, but not tomorrow. You wake up, sunlight filters through the blinds, you stretch, and instantly a flood of memories returns. Last night's conversation, the book you read, the worry you carried to bed. But you don't remember today's lunch. You don't recall the phone call you'll get this afternoon. You can't feel the joy or sorrow that hasn't happened yet. Why? Why does your mind reach backward, but never forward? At first glance, this seems obvious. The future hasn't occurred. There's nothing to remember. But in a block universe where past, present, and future all exist, that answer isn't enough. If tomorrow is just as real as yesterday, just located elsewhere in space-time, why can't your brain access it? The answer isn't in metaphysics, it's in thermodynamics. In the way your brain records information. Every memory you have is a physical trace, a pattern of strengthened synapses, a cascade of proteins, a rearrangement of molecules in your neurons, and creating that trace costs energy. It increases entropy. When you see a face, photons hit your retina, triggering electrochemical signals that ripple through your brain. Heat is dissipated. Molecules shift. Disorder grows, just a little, but irreversibly. That's the price of memory. And it only works in one direction, toward higher entropy. Imagine trying to remember the future, to form a neural trace of an event that hasn't happened. For that to work, your brain would need to anticipate the exact state of the world at a future moment and encode it now. But the future isn't determined in detail. Quantum uncertainty, chaos, and free will, if it exists, ensure that countless futures are possible. Your brain can predict, based on patterns, but it can't record what hasn't left a thermodynamic trace. Because recording requires interaction, and interaction requires entropy to increase. This is why perception itself is asymmetric. Light from a star travels for thousands of years, then hits your eye. That interaction creates a record, a signal in your optic nerve, a memory in your cortex. But light doesn't travel from your eye to the star, not because physics forbids it, but because such a process would require the star to absorb a coherent signal from your retina, decreasing entropy in the process. Statistically impossible, so your senses only gather information from the past. Your brain is a historian, not a prophet. Even dreams, which feel like glimpses of alternate realities, are stitched together from past experiences. Your mind remixes old fragments. It doesn't download tomorrow. And when you imagine the future, you're not seeing it. You're simulating it, using memories as building blocks. That simulation is creative, powerful, essential for survival, but it's not memory. It's projection. This thermodynamic basis for memory explains something deeper, why consciousness feels like a flow. Your brain doesn't experience time as a series of snapshots. It integrates sensory input over short windows, about 3 seconds, creating a seamless present. But that present is always slightly in the past. Neural processing takes time. What you feel now actually happened a fraction of a second ago. And that delay is bridged by memory, by the brain's constant updating of a coherent narrative. A narrative that only runs one way. Philosophers once wondered if time's flow was purely psychological. Physics now suggests the opposite. Our psychology is shaped by time's thermodynamic flow. We remember the past because the past left traces. We anticipate the future because the future is open full of possibilities that haven't yet collapsed into irreversible facts. And that openness is only possible because entropy was low at the beginning. So your grief over a lost moment, your regret over a wrong choice, your hope for what's ahead, all are echoes of the Big Bang's smooth beginning. You are not separate from cosmic history. You are a localized expression of it, a pocket of awareness riding the wave of increasing entropy, recording, feeling, choosing, in the brief era when the universe still has stories to tell. But what happens when that era ends? When stars fade, black holes evaporate, and even memory becomes impossible. What does time mean then? To find out, we must look to the final chapter of the cosmos, not with fear, but with awe. Because even in the end, the arrow has a purpose. Picture the universe 10 trillion years from now. The Milky Way and Andromeda have long since merged into a single aging galaxy, Milkdromeda. But even that is fading. Star formation has ceased. The gas clouds that once birthed suns have been exhausted, blown away, or locked in dead stellar remnants. The night sky is no longer speckled with light. It is almost black. Only the dim red glow of the longest-lived stars, small, cool red dwarfs, flickers in the void, and even they will burn out, one by one, over trillions more years. This is the era of decay, the long descent toward equilibrium. By this time, all planets will have either been swallowed by dying stars, ejected into interstellar space, or eroded into dust. Any life that once thrived will be gone unless it found a way to escape into artificial habitats, drawing energy from black holes or proton decay. But even those refugees are temporary, because entropy keeps rising, and time's arrow keeps pointing forward towards stillness. After the last star dies, the universe enters the degenerate era. It's populated only by corpses, white dwarfs, neutron stars, and black holes. Cold, dark, silent. White dwarfs slowly cool into black dwarfs, crystalline spheres of carbon and oxygen, radiating their last heat into the void over timescales so vast they dwarf the current age of the cosmos. Neutron stars spin down. Their magnetic fields fade. They become inert. And black holes, those entropy champions, begin their slow evaporation via Hawking radiation. A stellar mass black hole takes about 10 to the power of 67 years to vanish. Supermassive ones, 10 to the power of 100. Imagine that number. If you counted 1 digit per second, you'd need more time than the universe has existed just to speak it. As each black hole evaporates, it releases its stored entropy back into space. Not as structure, not as information we could read, but as a whisper of random particles and photons redshifted into oblivion by the expanding cosmos. And then, silence. The dark era begins. No stars, no black holes, no heat sources, just a near-perfect vacuum, filled with an ever-thinning sea of photons, electrons, positrons, and perhaps the ghostly remnants of dark matter. Temperatures approach absolute zero. Not quite, quantum fluctuations prevent true zero, but so close that no meaningful work can be done. No engines can run. No thoughts can form. No memories can be made. In this state, the universe reaches maximum entropy, thermal equilibrium, the end of the thermodynamic arrow. Time still exists, space-time continues, but it has no direction, no cause, no effect. A photon might drift for eons without ever hitting anything. An electron and positron might randomly meet and annihilate, producing a flash of light, but with no one to see it and no structure to record it, the event leaves no trace. It's as if it never happened. Some theories suggest that in this eternal stillness, quantum fluctuations could, over timescales beyond comprehension, spawn a new universe. A random bubble of low entropy inflating into a new Big Bang. But even if true, that new cosmos would be causally disconnected from ours. Our story would be over, and in our universe, time would have lost its meaning. Not because it stopped, but because nothing changes in a way that matters. This is the ultimate fate implied by the second law. Not fire, not collapse, but fade. A slow, quiet unwinding of all structure, all difference, all story. And yet, this ending is only possible because of the beginning. Because the universe started in such a special state, it had room to evolve, room for stars to shine, room for life to wonder, room for you to sit here reading these words, feeling the weight of time passing. The heat death isn't tragic. It's the natural conclusion of a cosmos that began with a whisper of order. And in that arc, from smooth beginning to silent end, lies the full sweep of time's arrow, unbreakable, unrepeatable, sacred in its finality. But we are not at the end. We are in the middle, in the only era when the universe can look back at itself, when stardust can become mind, when broken teacups can be mourned, and new ones can be filled with warmth. And that brings us to the final truth. Time's arrow doesn't just take. It gives. It gives us urgency. It gives us meaning. It gives us the chance to choose. Knowing we won't get a second try. So what do we do with this one-way journey? That's not a question for physics. It's a question for us. You stand on a beach at dawn. The tide is going out. Waves retreat, leaving patterns in the sand, ripples, shells, footprints. You know they won't last. The next wave will erase them. The wind will scatter them. Time will take them as it takes everything. And yet, you bend down. You pick up a shell. You hold it in your palm, cool, fragile, perfect. For a moment, it exists, not forever, but now. That's the paradox of time's arrow. It steals, it erases, it carries everything towards silence. But it also creates. Because without irreversibility, there would be no change, no growth, no learning, no love that deepens with years, no art born from loss, no courage that chooses kindness, knowing it can't be undone. A universe that could rewind would be a universe without consequence, and without consequence there is no meaning. We often mourn time's one-way flow, as if it were a prison. But what if it's a gift? The gift of a story that moves. The gift of a life that matters, because it ends. Think of a symphony. Its beauty doesn't lie in the final note alone, but in the journey from first to last, each chord leading inevitably to the next, never repeating, never retreating. You can't replay the third movement without living through the second, And that's what makes it powerful. Our lives are like that. Every choice, every wound, every act of forgiveness, it all flows in one direction, building a narrative that could not exist in a timeless void. Physics tells us we cannot go back, but it also tells us something quieter, more profound. We are here because the universe began in a state of grace. A state so improbable, so finely tuned, that it allowed entropy to rise, not as a curse, but as a canvas. On that canvas, gravity painted galaxies. Chemistry wrote the code of life. Evolution composed minds that could ask, why? And in asking, we became part of the story, not just observers, but participants. So what do we do with this knowledge? We don't rage against time's arrow. We align with it. We create what only irreversible beings can create. A letter to someone we'll never see again. A tree planted for shade we'll never sit under. A truth spoken, even when it costs us. These acts have weight because they can't be undone. They ripple forward into a future we won't see, but someone might. And in the grand cosmic arc, from the smooth fire of the Big Bang to the cold silence of heat death, our brief flicker of consciousness is not an accident. It's the universe becoming aware of itself, feeling its own passage, mourning its losses, celebrating its wonders. All because time only goes one way. So the next time you watch a teacup fall, don't just see the break, see the story it represents, the fragility, the beauty, the fact that it mattered enough to be held. And then, fill another cup, warm your hands, share it with someone, because the arrow still flies, and we are still here, moving forward, together, in the only direction that gives us meaning.